kind of lens do you see up here? There's two names for it. Give me one. We can call this a converging lens. Why do we call it, Benton, a converging lens?
Because the lines like...
Yes. Okay. He's using sign language right now, but yes, he's right. Rays of light converge or come together as a result of this lens. They refract and they come together. They converge. What's the other name for this lens? Convex. I will usually call it converging because I think that's a better name for it. That's what describes in a better way what's actually happening here. As Benton said, the rays of light converge. But we do also call it convex. Be prepared to see either one of those and recognize the name of that. Now be careful, because when we start talking about mirrors over the next couple of days, not today, but over the next couple of days, a converging mirror is a concave mirror. A converging lens is a convex lens. Yep?
So do all like convex lenses flip the image upside down?
No. Well, all of them do in certain circumstances, right? The question, if you didn't hear it, guys, was do all convex lenses flip things upside down? It depends upon where you put the object. If the object is far away from the convex lens or from the converging lens, then yes, the image will be flipped over no matter what. But if it's close enough, then the image will be right side up. And we see that as we go through our ray diagrams. If you have a convex lens, the focal length may be different. Okay, the shape of it may be a little bit different, but in the end, the same basic properties apply, just in different places, that's all. So this is a converging lens, a convex lens. Let's label a couple points on this converging lens here. What's this thing that we call in the middle here? No, it's not the focal point. It's the optical center, yeah. The optical center, sometimes we call it the OC. This is the principal axis. Sometimes we just call it the PA. This is the focal point. This is where rays, we talked about this yesterday, right? Where rays that are parallel will converge, they'll come together. This is 2F. This is just twice the distance. It's used as a spacer, that's all. Over here, I'm going to call this F in quotation marks, because it's not actually F. It's not actually where the rays focus or where they come together. It's just the same distance from the lens as the real focal point is on the other side. So we'll label it F, but put quotation marks around it to remind us that it's not actually the focal point. And same deal right here. We'll call this 2F in quotation marks because it's just the same distance as 2F is on the other side. Now, there are millions of rays of light that are reflecting off of this object. Millions. And each one of them refracts in a different way through this glass or acrylic or plastic lens. I want to pick two rays, just two. That's enough to tell me what the image is going to look like, and two of them in particular are very predictable. What's the first one that I'm going to draw? Yeah, the ray of light that reflects off of the top of the object and goes straight across, it's parallel to the principal axis. That ray will refract or bend as a result of going through the lens where? Through the focal point, yeah. Now, I told you yesterday that I lied a little bit, kind of owned a lie, a little bit of a lie. We said that it doesn't really go to the middle of the lens and then down like this. It really bends when it hits the boundary between the air and the glass, and then bends again when it hits the boundary between the glass and the air. But we draw it this way because it's the same effect. It's the exact same end point, and it's easier to draw it this way. So we'll continue to draw it this way, even though that's not really the way it's actually happening. There's two refractions rather than one refraction as we have it drawn here. Where does that second ray go? From the top of the object where? To where? Yeah, it goes through the optical center, down through here, and it keeps going straight through that optical center. Not really. It bends and then bends again, but the effect of it is that it goes straight through the optical center. Now this is our object. Our object always starts at the principal axis and ends where the rays start. The image of that object is going to be formed right here, from the principal axis to where the rays come together. That's my image. Red is my image, black is my object. Now, I want you to compare the image to the object here in terms of size. This red image, how does it compare in size to this black object? Is this red arrow bigger than the black arrow? Is it smaller than the black arrow? Or is this red arrow the same size as the black arrow? It's larger. Yeah, it's larger, it's bigger. Is this red arrow relative to the black arrow, is it right side up or is it upside down? It's upside down. We can call that upside down and we can call that inverted, whatever we want, as long as we mean the same thing, right? And the last one, is it real or virtual? This is a real image. What does a real image mean? It can be projected onto a screen. We don't have to project it onto a screen. We can look through the lens to see it, but we can, if we want to, project it onto a screen. Now, what in this diagram indicates to you that we have a real image here, that we can project it onto a screen? Yeah, the lines are solid. When solid lines intersect, it's going to be a real image. Good? I want to draw 2 more ray diagrams here. Here's the next one. This time my object is really, really close to the lens. Let's draw the same 2 rays. First one is parallel to the principal axis. Where does it go from there? Through the focal point. And this is the focal point, right? Not this. This is 2F. Okay, this is the focal point right here. Second ray is going to go where? Tim, where's the second ray going to go? Yeah, and it's as if it goes straight through the optical center. They don't come together on the right-hand side, right? So we're going to extend those rays back like this. We do that, we find that they're going to intersect back here somewhere behind the object. Red is our image, black is our object. How does that image compare to the object? Is the image, the red, bigger or smaller than the object? It's bigger, it's larger. And 2, is it upright or inverted? It's upright. And 3, is it real or is it virtual? It's virtual, which means we cannot project it onto a screen. We can see it, but in order to see it, we have to physically look through the lens like a magnifying glass in order to see it. It's virtual. How do you know that it's virtual? What on this diagram indicates that it's a virtual image, that we can't project it onto a screen? Yeah, what about them? Yeah, dotted lines intersect, it's virtual, and in the last one we had solid lines intersect, that means it's a real image. Yep. They won't draw it for you. Yeah, they're not going to give you a ray diagram. If you see a ray diagram on the diploma, it's going to be you that draws the ray diagram, so don't worry about that. But I will say, it is a good question. I will say that if you ever see somebody else drawing a ray diagram, they may not necessarily use dotted lines like I did. Okay, that's my little thing, so that we can distinguish between real and virtual. So somebody else may do that, somebody else may not do that. Just be prepared for that, okay? You know, I mean, you could modify somebody else's diagram to make it dotted lines and to tell you whether it's real or virtual, though, right? If you had to. You won't see that on the diploma, though. Okay, if you see a ray diagram on the diploma, it'll be because you drew one on the diploma. Okay, one more that I want to draw here. Let's pick this one right here. What type of lens do we have here, by the way? 2 names for it. One is concave. The other is called diverging. And we call this diverging because rays of light go through this and spread apart, diverge. This is our optical center again. This is F. This is actually F this time, not quotation marks F. And this is actually 2F rather than quotation marks 2F. First ray goes from the top of the object parallel to the principal axis like it did last time. But this time it does not go down through a focal point that doesn't exist on the right-hand side. Rather, it goes up away from that focal point. What you want to do when you're drawing this is to take a ruler and have it go from this dot to here, and then just draw the dotted line and the solid line from there. Second ray is going to go, Benton? Yeah, down through the optical center. They converge over here. You can see that the image is formed right there, and the attributes or the characteristics of that image are that it is smaller, right? This is less than half the size of the object. It is upright or inverted? Upright. And it is virtual. How do you know it's virtual, Mateo? Yeah, because dotted lines intersect. We can see this image, but we have to look through the lens in order to see this focused image. This is These are the same characteristics that we get anytime we have a diverging lens, right? No matter where the object is placed, we get the same three characteristics. Now, over the next few days, we're going to look at curved mirrors. And you're going to draw some ray diagrams for curved mirrors. And like in a few minutes, we're going to do mathematics of curved lenses. You'll also do, in a few days, mathematics of curved mirrors. You should, by this point, at least hopefully by this point, starting to notice some patterns. Firstly, we talked about this one yesterday. If you remember the ray diagrams in order, you'll remember that the first three ray diagrams, in the first three ray diagrams, we produced a real image, right? In the fourth ray diagram, there was no image. This is the easy one because there was no image. That's the one where the rays didn't come together. No characteristics of that one at all. 5, 6, 7, 8, and 9, and 10, they all produced a virtual image. Now, the real image, if you remember back to those first three ray diagrams, the real image was always upside down. So a real image will always be inverted. And the last 6 diagrams, the virtual image will always be upright. It's not virtual because it's upright. It's not real because it's inverted. It just happens to be that when you get a real image, it will always be inverted. And when you get a virtual image, it will always be upright. So, first 3, real. Remember, though, the image is getting bigger, right? We're going from small to same size to bigger. And then it's the kaboom one, diagram number 4. And then we have a virtual image for the other 6. And in all 6 cases, it's upright. Sometimes we can remember some patterns here like this and avoid drawing a ray diagram. Don't have to. You can draw a ray diagram if you want, but sometimes we can save ourselves a little bit of time and effort by just remembering a few patterns here. All right, what I want to show you today is a little bit of math that we will use to analyze these problems. We've solved them graphically yesterday by drawing ray diagrams. Today we're going to solve them mathematically. The only page of notes you're going to get today, besides a couple example problems. One little table and then a couple equations that we put at the top. The 2 equations that we're going to use to solve all these problems are as follows. The first one, which we often call the thin lens equation, says 1 over f is equal to 1 over do plus 1 over di. What do you think f stands for? Not the frequency, no. No. F stands for the focal length. Frequency does stand, F does stand for frequency in other contexts, right? The Michelson experiment and so on, but in this context, it would not be the frequency at all, not related at all to the frequency. It's the focal length. The focal length is the distance from the lens to the focal point. DO would stand for, yeah, it's called the object distance, and the object distance is the distance from the object, whatever it is that we're trying to see through the lens. This is from the object to the lens itself. And DI would stand for the, probably figure this one out now. Nick, what do you think DI stands for? DO is the object distance, DI would be the, anyone? Oh. Going to be the image distance. The distance from the lens to wherever the image is formed. Okay, that's one equation. Some of you are starting to panic a little bit right now because it's pretty good fractions involved there. Don't worry about that. I got a little trick for you. So you don't have to deal with fractions too much. The other equation says this: m is equal to hi over ho, and that's equal to negative di over do. I'm color coding these. You'll see why in just a moment here. We know di, what di means, image distance. Do means object distance. Hi means, anybody want to take a stab at that one? Yeah, it's the image height, the height of the image, how tall the image is. And HO would be the, yeah, that one's easy now, right? It's the object height. Now M, that one might be a little less obvious. M stands for something called magnification. Sometimes you see it as a lowercase m, sometimes you see it as an uppercase m, whatever, same thing. The magnification just means how big the image is compared to the object. If the magnification is 2, then that means the image is twice as big as the object. If the magnification is 17, then the image is 17 times bigger than the object. If the magnification is 0.5, then the image is half as big as the object. So we're going to say if m is less than 1, we're going to say the image is smaller than the object. And if m is greater than 1, the image is larger than the object. Right? So if I get a magnification of 2, smaller or bigger? Bigger. Magnification of 12, smaller or bigger? Bigger. If I get a magnification of 0.75, smaller or bigger? Smaller. It's 3/4 the size of the object. What about units? What units do I use for focal length and object distance and image distance and HI and HO? They're all distances, right? What units do you think I use? Could use meters. They all cancel, yeah. They all cancel, so it doesn't really matter what you use. We're going to say any units here. By any units, I mean any distance units, including inches if you wanted to, as long as you're consistent through a problem. Now, honestly, you're probably going to use centimeters more than anything else here, just because that's what distances are commonly given to you in, is centimeters. Doesn't matter, though, whatever's convenient for you. There are no units associated with magnification because the units cancel. Centimeters over centimeters, cancel. Meters over meters, cancel. I want to complete this table now to show us when these variables that we just talked about should be positive and when they should be negative. You're going to see why now I've color-coded these, blue and green. All the variables that are in blue here, F, DO, and DI, have a similar reason for being positive or negative. They will all be positive if they are real. In other words, if we have a real focal point, the focal point will be, or the focal length will be positive. If we have a real object, then the object distance, which is the distance from the lens to the object, will be positive. If we have a real image, then the image distance, the distance from the image to the lens, will be positive. If we have a virtual focal point, then F will be negative. If we have a virtual object, then DO will be negative. And if we have a virtual image distance, or virtual image, I should say, then the image distance will be negative. We can clarify this a little bit. We will have a real focal point, a positive focal point, a real focal point, if we have a converging lens, or mirror for that matter, as we'll talk about over the upcoming days. It will be a virtual focal point or a negative focal length if we have a diverging lens, or for that matter, a diverging mirror, as you'll learn over the next few days. The object distance is positive if the object is real. Here's the good news. For us in Physics 30, the object will always be real, and therefore the object distance will always be positive. The object will never be virtual for us in Physics 30. It is possible to have a virtual object and therefore a negative DO, but it won't happen for us. You can, if you're doing a two-lens system like a microscope with an objective lens and an ocular lens, two lenses, the image from one of the lenses becomes the object for the second lens, and it's possible for that object for the second lens to be a virtual object and therefore a negative DO. But we don't have to deal with two lens systems, so we're never going to have to see that in Physics 30. But do understand that if you take physics course next year, you might see a situation where there's a negative DO or a virtual object. DI is positive, the image distance is positive if you have a real image. And you have a real image in, well, 3 of the 10 ray diagrams. Right? Remember, 3 of the ray diagrams were virtual, 1 was no image, and then 6 were virtual images. If you got to guess whether to make DI positive or negative, what should you guess? Negative. In one of the ray diagrams, 1 of the 10, there is no image. So we're left with 9 ray diagrams where there's an image. In 3 of those 9, the image is real, and in 6 of those 9, the image is virtual. So if you got to guess virtual, because you got a 66% chance at guessing correctly if you guess virtual. No guarantees by any means, but at least the odds are in your favor. There. Yep. Let's look at the other variables now. HO and HI. They're in green. All the green variables relate not to whether they're real or virtual, but relate to whether they're upright or inverted. If we have an upright object, which we normally do, then it's a positive object type. If we have an upright image, which we do 6 times out of 9, because remember, whenever we have a virtual image, it's going to be upright. Whenever we have an upright image, which is 2/3 of the time, it's going to be a positive HI. Now, when are we going to have a negative HO? If it's an inverted object, which isn't going to be very often, if ever. And when is HI going to be negative? If you have an inverted image. That's going to happen. That's going to happen about 33% of the time, because you get a real image, which is inverted, 3 times out of 9 for the ray diagrams. Finally, there is one more variable that we haven't put in this table yet. What is it? F, DO, DI, M, HI, HO, and M. M goes right here. Same as HI. If your image is right side up, M is going to be positive. If your image is upside down, M's going to be negative. So let's say now you get a magnification of +3. What does that mean? You get a magnification of +3. It means the image is 3 times bigger than the object. If you get a magnification that's +0.5, the image is half the size of the object or smaller, right? If you get an image that has a magnification of -3, what does that mean? No. If you have an image that has a magnification of -3, that means it is 3 times bigger, but upside down. Right? Magnification that is bigger than 1 is a larger image, 3, but it's negative, means it's upside down. If you get a magnification that's -0.25, then that means the image is 1/4 the size or smaller and upside down. Positive 0.25, 1/4 the size, but smaller, yes, 1/4 the size, and right side up because it was positive 0.25. Does that make sense? We're going to do 2 example problems right now. Then I'm going to set you free to work on a couple problems yourself. As you work on those problems, and as we go through these examples, don't be afraid to look at this table. Like, keep this table beside you. There's a reason why we write this down. On test day, you're not going to be able to look at it, right? But when you're practicing, when you're trying to get good at these questions, you should be looking at it. You shouldn't be trying to have it memorized the first time you do a question. All right, let's take a look at example number 1. It says, a converging lens. I'm not going to go any further right now. Beyond those 3 words, a converging lens. I circled this because I always want to circle what type of lens I have. How come? We have a converging lens, therefore, sorry, say it again? Yeah, refracts. Yeah, yes, it refracts downwards, which tells us that we have a positive focal point. Okay, that's the note that I want to make here. I want to get in the habit of doing this. Every time I see it's converging, diverging, convex, concave, I want to identify whether my focal length is positive or negative. Because look, even if this question said a diverging lens of focal length 24, it wouldn't tell you that it should be negative. But if it was diverging, we'd need to make it negative in order to get this right. So we want to get in the habit of identifying that so that we don't forget to add a negative when necessary. Okay, it's used to view an insect that's 18 centimeters in front of the lens. What's the image distance in the magnification? F is positive 24. Sometimes it's negative if it's a diverging lens. My object distance here, this is where the object is, the insect is, 18 centimeters in front of the lens. DO is always positive, right? Look at your table. Like DO is always positive for us in Physics 30. We're looking for the image distance, DI, and we're looking for the magnification. We only have two equations, right? Which one do you want to try first? Yeah, okay. The lens equation, 1 over F is equal to 1 over DO plus 1 over DI. 1 over 24 is equal to 1 over 18 plus 1 over DI. How many people feel like they're pretty good with fractions and can solve this? Oh, good. None of you. Oh, one. Oh, it's a question. Okay, Mateo, what's your question? No, you can't do that. Good idea, but man, it's sure nice if we could. That would make DI 6 if that was the case, right? It's not even close to 6. Not even close. But I am going to show you a little trick here. If I was a math teacher, I wouldn't do this. I would, honestly, I would love it if you could solve this the true mathematical way of finding the common denominator and then combining terms and so on. But that's a day or two lesson in adding fractions, and that's not the purpose of this class, okay? If you could do it, that's great. But if there's a little trick that I can show you to do it, then that's what we're going to do. So I'm going to show you that trick now. I want you to pull out your calculators, and I want you to follow along with me. In order to get DI by itself, I have to take the 1 over 18 over by subtracting, right? So it becomes 1 over 24 minus 1 over 18 equals 1 over DI. You agree with that? Okay, so here's how you're going to do that on your calculator. You could say bracket 1 over 24, bracket minus bracket 1 over 18. You can do that. Okay, I don't want to do that. There's an easier way of saying 1 over 24. 24x to the minus 1 is 1 over 24. 1 over 24 minus 1 over 18 equals negative 0.013889. And that's still equal to 1 over DI. So 1 over 24 minus 1 over 18 gives me 1 over DI. How do you solve for DI? Take the DI up and the 0.01 down. In other words, take 1 over this. X to the minus 1. So 1 over 24 minus 1 over 18, enter, and then say x to the minus 1, and you get a value of negative 72. That's my answer. My image distance is negative 72 centimeters. You guys do that? That's way easier than finding a common denominator, isn't it? Now, understand that when we do that, that only works if the numerator is 1, right? That only works if the numerator is 1. In the context of these questions, the numerator will always be 1. That's why I showed you this way of doing it. But this isn't going to solve all those math problems on your math test when you have to add or subtract fractions. Okay, I want to find the magnification now. So let's say now m is equal to, well, we could say hi over ho, but I don't know what those are. So I'll say negative di over do. That's the second part of that equation. M is equal to negative di over do. That's what? Negative di is 72 centimeters. Do is 18 centimeters. That gives me a value for the magnification of negative 4.0. Is that right? 72 divided by 18 is 4, but we have a negative there. Parker?
What did you do to get from the decimal?
Ben, what's wrong with that?
Because it's like negative
Yep.
di.
Yep. It's negative di, and di is negative 72, so it becomes negative 72. That gives me a value of positive 4. Yeah, you could just write 72, absolutely. I'm showing negative so that you understand where that positive comes from. But yeah, you could, if you're doing it yourself, just write positive, yeah. There are no units with this. I get a positive magnification of 4.0. Now, you weren't asked to identify the attributes or the characteristics of this, but we could do that. This tells us, the fact that it's 4 tells us that the image is bigger or larger. The fact that it's a positive magnification tells us that the image is, somebody said it? No. No. What is it? It's upright. Listen, it's okay if you don't remember all the sign conventions, right? That's why you're going to look at your table when you're solving these problems, right? And then you're going to get used to it, and then you're going to be good at it. We also know that it's what type of image based on the negative di. Cameron, what type of image is it? What type of image is it based on the negative di? Real or virtual? Yeah, a negative di tells me that it's virtual. So although you weren't asked for the characteristics of the attributes here, we can find them pretty easily if we remember the sign conventions, which we will with practice. Example number 2, then I'm going to call it a day here. This one says an object is located 32 centimeters in front of a lens. Doesn't say what kind of lens. Forms an image on a screen that's 8 centimeters from the lens. Why am I underlining that? Like, what's special about that little phrase there that's telling me something that I should know here? It's a real image because it's projected onto a screen. And if it's a real image, then that means that di is positive. Right? Real image, di is positive. What's the focal length? And again, the attributes of the characteristics here. Let's write down some givens here. We're going to say that the object distance is 32 centimeters. It's always positive. The image distance here is positive 8.0 centimeters. Okay, if it was a virtual image, then we would have made that negative 8. We want to find the focal length and the attributes. Let's say 1 over f is equal to 1 over do plus 1 over di. 1 over f is equal to 1 over 32 plus 1 over 8.0. Let's say 1 over 32 plus 1 over 8 gives me 0.15625. And now, Parker, how do I find f now? Once I've got 1 over f is 0.1565. Yeah. That number to the minus 1 gives me 6.4. So f is, I'm going to say positive 6.4. I don't need to write down the positive, right? Because not writing a negative means positive. But I just want to bring that positive right up front to make it more obvious. We get a positive focal length. That tells us that we have what type of lens? It tells us it's a real focal point or a convex or converging lens. Now, there is something else that tells us it's a converging lens. Remember, a diverging lens always produces a virtual image, right? So this has to be a converging lens even before we solve for anything, because converging lenses are the only things that can produce a real image. Now, what are the attributes? I think I'm going to have to do something else. Maybe find the magnification. We're going to say -8. Whoops. Over 32, which gives me -0.25 is my magnification. The 0.25 tells me that the image is what? No, 0.25 doesn't tell me it's inverted. 0.25 tells me it's 1/4 the size, or smaller. The negative tells me that it is inverted. And we already know that it's real, right? Because it's projected onto a screen. Here's your homework for tomorrow, and you can work on this for the next 10 minutes of class here. It is worksheet number 18. There's 4 questions on that worksheet. I'd like you to do, please, the first 2 questions tomorrow. Worksheet number 18, questions 1 and 2. And of course, we do have a quiz tomorrow as well, right? Quiz number 22 tomorrow, based on refraction that we checked over today.